Okay, so g-2 experiment. These experiments are performed in order to find the anomalous magnetic moment of muon, and the motivation for these experiments is that when we look at these kind of experiments. So if you look into the higher order corrections like this one, we eventually, when we can calculate the anomalous magnetic moment, which is for muon, it will be like g-2 over 2. So this will be the anomalous magnetic moment of muon. Eventually, when they calculate the anomalous magnetic moment of muon, there's a slight difference between the actual value and the predicted value. Let me write that for you. Okay, so experimentally they found this value, and these experiments are also called precision experiments, and the last one they did at AGS Brookhaven laboratory in alternating gradient synchrotron. They measured the value of mu, and there is another experiment which will be performed in I think 2025. Well, the point of, or the motivation for finding the value of a mu, which is the anomalous magnetic moment of muon, is to get as much as precise they can the value of anomalous magnetic moment of the muon. Because why they are doing this? Because when we see the theoretical value, of a mu, and what we found in experimental results, there is a difference. And in these two calculations, the difference is 2.7 sigma, that is this number. And the experimentally found values are 2.7 sigma away from the standard model predictions. Now one can say that there could be a problem in the theory, but let me tell you, the quantum electrodynamics is one of the most successful theories we have so far. So the thing is, again, the motivation for this experiment is that actually this difference can give us a hint for some new physics. And of course there are theories beyond the standard model, like the SUSY, supersymmetric theories, and there is a theory in which supersymmetric theory in which there are bosons corresponding to fermions and fermions corresponding to bosons. So for every fermion there is a boson, so they have a lot of particles anyway. And if this difference is there, and right now they are at right now they are not at 2.7. Currently they are at, I think, 9 sigma, and which clearly tells us that there is something which is missing, and that something could come from those beyond the standard model theories. Anyway, the point is that this experiment is important in that sense that there is some new physics that we don't know. That's why they perform this experiment to find this the value of the anomalous magnetic moment of muon, and they find it very precisely. And now they I mean, the result of this experiment is that, yeah, there is some new physics. Anyway, now I'm going to tell you how do they measure this anomalous magnetic moment. Let's jump into that. Okay, so the experimental setup for this kind of experiment is like that. They sent a high energy proton beam onto a fixed target, and after interaction a lot of pions are produced, and then these pions later decay into muons, and we get a muon beam. This muon beam is sent into a toroidal magnetic field, and that is also that magnetic field is shaped like a donut. If you see a toroid, it is shaped like a donut. So yeah, donut shaped magnetic field. They send these muon beams into a donut shaped magnetic field, and they measure the precession frequency or the wobbling of muons while they pass through the this toroidal magnetic field. Okay, eventually, because muons are heavy particles and they decay into electrons after approximately 10 to the minus 7 seconds. I think I'm right here. Well, eventually they decay into electrons, and these electrons can be captured into electromagnetic calorimeters, where they can these electrons carry all the information of muon, like their spin or their wobbling frequency, etc. So we can get a lot of information from these electrons. So they are captured in electromagnetic calorimeters. Okay, so now how do we measure the wobbling frequency of electrons of muons? So this is the wobbling or the precession frequency of muons. This is we can write it as a difference of the precession frequency of muons minus the precession frequency of cyclotron, and it can be written as E/m ratio times anomalous magnetic moment of muon times magnetic field minus a mu minus 1 divided by 1 minus gamma square into E cross B. Okay, so here we have a lot of variables. A mu, okay, highlight them, wobble frequency or the precession frequency, A mu, E and B. Now if you are an experimental physicist, or even if you're not an experimental physicist, you want your job to be easy. So in order to cancel out this effect, E cross B effect, so they choose a specific form momentum, and the amount of this form momentum is 3.09 GeV, or we can say that if we choose gamma is equal to 1 over A mu plus 1 in the square root, and if we choose this value of the gamma, and gamma is eventually related to the boost. Anyway, yeah, when we put this value here, so okay, let's do it. Okay, so I'm just writing this term here, a mu minus 1 upon 1 minus gamma square would be just 1 upon a mu plus 1. So let's do a little algebra. A mu minus 1 divided by a mu minus 1 plus a mu minus a mu divided by 2 a mu minus 1, and again if we take the 2a mu minus 1, so here we will get a mu into 2a mu minus 1 minus a mu, so a mu square minus 2a mu square minus a mu minus a mu 2a mu minus 1 and we get 2a mu square 2a mu square minus 2a mu, and I think I'm missing something, but anyway, let's see. So yeah, I did a mistake. Here we had gamma square minus 1, and I'm doing the calculations again. Anyway, this was simple. I was just messing up. Anyway, yeah. So yeah, if we choose gamma equal to 1 over a mu plus 1, or if we talk in terms of the momenta, if we take this specific momenta, then we will get rid of this E cross P. Anyway, so after doing that, we can write a mu as precision frequency divided by E over mu c, E over mu c, yeah, and into the magnetic field. So this is how we calculate the anomalous magnetic moment of muon. I think, yeah, that's it. This is how a typical g-2 experiment is performed, and these are some of the rough calculations that did do. And yeah, this was done in AGS, which is in Brookhaven, alternating gradient synchrotron. Anyway, yeah, that's it.